So let's talk about solutions. Maybe I can do it this way. Early on, we talked about mixtures, heterogeneous versus homogeneous mixtures. And I drew your attention to the fact that homogeneous mixtures also go by the name of solutions. That is, they're uniform throughout. So we're going to focus on solutions, maybe generally at first, and then we'll direct our focus on aqueous solutions only. They're the predominant ones that even chemists deal with, but especially healthcare professionals. Aqueous solutions are it. All right. These homogeneous mixtures can come in different flavors. You can combine any phases together, solid, liquid, or gas, and get a solution, potentially get a solution. What we normally think of as a solution is dissolving a solid in a liquid, like throwing sugar into water or salt into water. But that's only one type of solution. That's the solid phase in a liquid phase. But you can get liquid-liquid, like alcoholic beverages. They've got ethanol as a liquid, water as a liquid. You can get gases dissolved in liquids. That's the foundation for pop. Gases and gases. We're breathing a solution right now. It's predominantly nitrogen and oxygen. And as a side note, anytime you combine two or more gases together, you always get a solution. There's no room for heterogeneity in gas mixtures. Predominantly because there's plenty of room for everybody. The gas molecules or atoms are so far apart, you can slide anybody in there. So gases always form solutions. You can get solutions of two solids, like for instance alloys. Metallic alloys are solutions of two solids. Brass is a solution of predominantly copper with a good bit of nickel in it. And then I think they add some other components too. That's the thing about alloys. You say steel is iron and carbon, but that's only the base mixture. They add lots of other stuff to them. Like stainless steel has lots of chromium in it. High strength steel that they're using in automobiles now has some other added components, other metals. So solutions don't have to have just two components. They can have any number of components mixed together as long as they're homogeneous. Now, terminology. Solvent and solute. The solvent is, at least in the beginning, when you start to make your solution, the solvent is the major component. So if you're going to make sugar water for your hummingbird feeder, well, that's a bad example. It depends on how you make it. But if you do, I'm going to continue with that, but maybe not for the hummingbird feeder. If you take water and you start dumping sugar into it, you know that it goes into solution pretty fast. Pretty soon it's a homogeneous mixture. If you keep adding sugar to it and you're keeping track of how much, eventually you'll reach a point where you'll have more sugar in there than you do water. But at that point, we still consider the water as the solvent. And the solute is what you add into it. It's usually the minor component, a minor component. And in our example, that was sucrose, table sugar. And that's a solid until you mix them together. But actually for most solutions, the minor component always stays minor. You reach a point where if you add any more solute of a particular kind to the solution, then it won't take any more. You've reached what we call saturation. But sugar is a special character. You can put a lot more sugar in water than you have water eventually. In fact, that's how sometimes some businesses, some companies use sugar in the liquid form because it's easier to transport and move around once it gets to the location. I've got this book at home. It's called "This is Liquid Sugar," and they have concentrated solutions of sugar. It's easier to pump and move around, and maybe the process doesn't need for it to be dewatered. Maybe just go straight into the product stream. But you can only have one solvent, but you can have many solutes. Okay? So you have to identify which one's the solvent and everybody else is the solute. You can have 1, 2, 3. Sky's the limit. That's an example. I don't know what they're dumping in there. Doesn't say. But they're putting a solid in the liquid, and eventually you'll see that you have a solution. And how do we tell? I think I've got a slide on this, but stream of consciousness. When you have say, making a solution here, how do you tell if that's a solution or it's just a suspension of some kind? Shoot, my mind's gone blank. I had the word ready to go. Let me see if I've got it over here again. Oh, it just came to me. You use what's called the Tyndall effect. If you have a bright light, laser beams work best, but a flashlight will work. And it makes a beam, and your eyeball's over here, and you can see the beam coming out the other side. But if you move your eyeball down here, and this is 3 dimensions, actually you move it out here like this. If you can't see anything from the side, that means there's no, the light beam is not reflected off of particles. That's the key. If you can see here that it's not a solution, that's the Tyndall effect. And hopefully I'll have a slide on it. But what it does is those particles are not in the matrix in between the solvent molecules. So they're not, they might attenuate the beam out this side, but you won't be able to see them reflected off the particles on this side. This would be a suspension if you can see them, and it would be a true solution if you can't see them this way. In fact, in my general chemistry class, we do a titration where we add a certain amount of solution in increments to a container, and what we're looking for is the formation of a precipitate, silver chloride. Well, it's very difficult to see it in a lit room, and even if you turn off the lights, and well, actually that's what we do. We turn off the light and we shine a flashlight through the solution. And when that solid forms, it's not a solution anymore, right? It's a suspension, and you can see it in the beam. We use the Tyndall effect to detect where is exactly the endpoint for that reaction. Okay, so I spent enough time on that slide. Characteristics of a solution, we mentioned the first one already. It has to have 2 components, but it can have more. It can have variable composition. So what does that mean? That means you can add more solute to it and change the percentage of the solute in the solution. So solutions can have variable composition. And their properties can change as you change that composition. For instance, we're going to use one of those properties today in the lab, the freezing point of the solution or the pure substance. We're going to compare the two. The freezing point changes when you add more solute in it. In fact, the freezing point is depressed and it'll freeze. It'll become solid, the liquid becomes solid at a lower temperature when you add solute to it. So we're going to use that property to determine how many moles of the solute we actually added to it. And I'll discuss that prior to the lab. When a solute goes into solution, when it actually produces a solution in the solvent, it is present as individual particles of that substance. Now, if it's a molecular substance, those molecules will retain their chemical identity. If they're free atoms, like we put nickel dissolved in copper, the nickel atoms they retain their identity in that solution. Or if it's an ionic compound like sodium chloride and we put it in water, the ionic compounds have to break apart in order to go into solution. So you have free sodium ions and free chloride ions in that aqueous solution. This is a given. Solutes remain uniformly distributed and they will not settle out over time. That's key. They will not settle. If you have a suspension, then eventually whatever you put in there, if it's say it's a solid and a liquid, then the solid will settle out. Like you try to mix sand in the water, mix it up, you see pretty quickly that once you stop stirring it, the sand settles. That's a suspension. And this is not a chemical process. I mean, there's some chemistry involved, but we classify it as a physical process when you form a solution because you're not changing the identity of the components. Both the solute and the solvent and any of the solutes retain their chemical identity. So that means you can separate them using physical means. How do you get table salt back from a solution in water? You just evaporate the water, and there's your salt. Right? We did that one, didn't we? Yeah. We mixed, I think it was sand and salt together. Yeah. So you can separate those by physical means. Okay. In a homogeneous mixture containing 80 milliliters of water and 20 milliliters of alcohol, identify the solvent and the solute. Well, based on our definition, the solvent has to be water. It's the major component. And the solute is the alcohol. See if I can get this to work. Okay, there's another term. I sort of alluded to it when I talked about saturation. A solution, the solute has a given solubility. What that means is how much, what's the maximum amount of solute that you can put in the solvent. And beyond that, you can't put any more. That's termed the solubility of the solute in that given solvent. Solubility is dependent upon what's already in there. If there's a solvent there, the pure solvent, and you put one solute in there, that will be a given solubility. So many grams per 100 milliliters is one way of expressing it. But if there are other solutes in there already, that may enhance or depress the amount of solute that you want to put in there, a different compound that you want to put in there. So the solubility is dependent upon both the solvent and any other solutes that are in there already. Okay. In this class, we're not going to go too deeply into that. In my general chemistry class, we actually calculate the solubility of a solute when there's already something else in there. So it can be done. It's just we need 2 semesters to get everything in that detail that we get in this class in 1 semester. Temperature has an effect on solubility. Generally speaking, most solids become more soluble in water when you increase the temperature. That's not always the case, and it's not predictable. There's no way we can tell exactly. There are some theories as to why it happens, but the only way to tell for sure is to do an experiment. Dissolve so much in there and increase the temperature. Can you put more in, or have you reached solubility limit and saturation, and as you increase the temperature, you start to form a precipitate, drops out of solution. Gases, on the other hand, tend to be less soluble as you increase the temperature. So that's why if you have a bottle of pop in the refrigerator and you pull it out of the refrigerator and you hadn't opened it yet, this is first, you open it up and it goes psst, just a little bit of gas release. And you go and take the same product in a different bottle that's been sitting at room temperature, you crack it and it goes psh. Right? Higher temperature means more gas comes out of solution, so you have more pressure in that headspace. That's why if I'm going to drink any pop, which I don't do much anymore, I take it and stick it in the refrigerator for a couple of hours, let it cool down first. Because I mean that's one of the main purposes of pop is the fizz. So I put it in the refrigerator first, so when I crack it, I don't lose all my gas. That's why I hate going to picnics, because they always have, well, not always, but they usually have bottles sitting out on the table, never been opened, and they're room temperature or higher because it's in the summer. So first person that cracks it open gets most of the fizz in their glass, and everybody else has to drink flat pop. But that's characteristic. Solubilities of gases in water are nearly always less soluble as you increase the temperature. These are some examples. These are solids on the left-hand side, and temperatures for aqueous solution, and their solubilities are given in terms of grams of solute per 100 grams of water. 100 milliliters of water would be comparable. And if you go to a reference manual and you're looking up solubilities of different compounds in water, they're going to be listed that way, so many grams per 100 milliliters at a given temperature. If it doesn't say what the temperature is, assume it's standard temperature, and for these solubilities, the standard temperature is 25 degrees Celsius. But if it says the temperature, then okay, that's fine. But you may want to know the solubility. So you've got an experiment you want to run, and you need a solution of, say, lead 2 bromide, the first one on the list. But the solution that you need to prepare needs to have 6 grams per 100 milliliters. You know you can't do it, right? Because your experiment's going to be done at room temperature, and the solubility is only 1.94. So you know, what am I going to do? You may have to go back to the drawing board and devise a different experiment. But that lets you know in advance that you can't do it. Yeah, pointed out calcium acetate. It's not on that list. Calcium acetate is one of those compounds that becomes less soluble as the temperature increases. So what's the effect of pressure on solubility? Well, for solids and liquids, no effect. The pressure doesn't change their solubility at all. But for gases, it is significantly different. If you increase the pressure on the solvent with the gas that you want to put in solution, more of it goes into solution. So solubility increases with pressure of the gas in the headspace. And this is the law that governs that. We've covered all the gas laws, right? Boyle's law, Charles' law, Avogadro's law, the combined law, the ideal gas equation. But this one has to do, and this is a law, it just states this is what happens. It doesn't explain why. Henry, I don't know if he was English or French, one or the other, but that was his last name, Henri. He was probably French. The amount of gas, the solubility, the concentration of your gas in solution can be determined if you have the constant value, H, the concentration, you need the constant value and the pressure of the gas. Now this constant value is going to vary. It's going to be particular for the gas that you're trying to put in a solution and the solvent. So when it says H is Henry's constant, it's constant, yes, but it's only constant for a particular combination of solvent and solute. But notice if you increase the pressure, you increase the concentration. So they're directly proportional to one another. And we could treat this the same way we did the gas laws, right? We could say, set them equal to H, right? If this is the initial and this is the final, then they're equal to each other, just like we did our gas laws. And you can say, I know the concentration now, I know what the pressure is, I want to increase the pressure to this, then I know what the concentration will be. All right. Oh, and by the way, I left out Dalton's law of partial pressures. If you know the partial pressure of that gas, this works for solution for multiple solutes as well. Like if you tried to put air into solution in water, then you'd have to consider the partial pressure of oxygen versus nitrogen. If you want oxygen, you have to take the total pressure and find out what the fraction of oxygen is to find out what its pressure is. The P is partial pressure for that particular gas. So here's a saturated solution. A saturated solution says you've got a solvent and you've got, say we've got a crystal here of sodium chloride. Right? So as it's sitting in the water, sodium ions and chloride ions are moving into solution. They're becoming hydrated. Okay, they're moving out like that. But at the same time, they can also return. Right? You can get some chloride ions returning and some sodium ions returning. In the beginning, when you first drop that crystal in, or that cube of salt, it's all one way, right? Because there are no sodium chloride ions in the solution yet. So they go into solution and they keep going until the solution can't hold anymore. And what that means, at the macroscopic level, we see that the cube shrinks and shrinks and shrinks and stops. Doesn't get any smaller. That's an indication that the solution is saturated. But on the microscopic level, what's happening is you're getting both ways are happening at the same rate. So you're getting some of these going into solution and they're coming back just as fast. At that point, the solution is saturated with your salt. Can't take anymore. And if you add more solid to it, it'll just sit there. It won't do anything. As long as you don't change the temperature. If you increase the temperature, then it'll start going into solution some more, because the solution can hold more. Now, the explanation for that has to do with kinetic energy, right? The kinetic molecular theory. We covered that for gases, didn't we? No? Maybe in the other class. Sorry. You're getting, as you increase the temperature of the solution, you're increasing the temperature of the solvent for sure, and those water molecules are moving a lot faster. So when they strike the surface of the crystal, they're hitting it with a lot more force, and they're knocking things loose. And they go into solution, and the kinetic energy is what keeps everything in solution. If you cool it down, then you lose that energy, and the solute starts dropping out of solution. Okay, so that's the best explanation I can give you in a shorthand for saturation of your solution. Now, if you want your solution to be saturated at room temperature, say 25 degrees or 20 degrees, whatever the case may be, what you may do is you look at the table, right? Go to your reference manual, find out what's the solubility at that temperature. If you want the solution to be saturated at that temperature, then you put enough in there plus a little extra. Put for saturation at that temperature, then put extra. Now heat it up. Make it hotter, get everything into solution, and then set it on your bench, covered of course, and just let it cool down to room temperature. And what will happen is anything that won't dissolve at that temperature will just drop out of solution, and you'll have a layer on the bottom of your beaker of the extra solid that won't go into solution now at that temperature. And at that point, you know your solution is saturated. Now, if you don't want to get any of those suspended particles and you want to deliver that solution for an experiment, you just run it through a filter, and it'll filter out the suspended solids if there are any. Okay, enough of that. The fly in the ointment, as they say, is that sometimes you can exceed the expected saturation point for a solute in a solution. We call that situation supersaturation. Now, how do you do it? Well, take that previous scenario. You heat up your solution with extra, and then you set your beaker down, and you let it cool very slowly. Supersaturated solutions are unstable, very unstable. So when you let it cool down, maybe it doesn't lose all that solute that's dissolved. At that point, you know it's supersaturated, and all you have to do is shake it or reach in there with your spatula and scratch the inside of the beaker, and it drops out of solution. All the extra comes out of solution like that. It doesn't like disturbances. Okay, unsaturated solutions are those that still have room for more. They've not reached saturation, so you can put more in them if you want. More terminology. If the amount of solute in your solution is approaching saturation, very high concentration relative to saturation, we call that concentrated. And if it's very low, it's just a little bit, it's more toward the starting point, so to speak, then that's a dilute solution. These are qualitative terms. So if I say I've got concentrated sulfuric acid in the bottle in the prep room, well, from experience, I know that that's probably 98% sulfuric acid. But if I say I've got concentrated hydrochloric acid in there, that's probably 70% by mass. So it's relative. The concentration is relative, that term. Now, if you want to concentrate a solution, you just remove the solvent. Right? And if it's an aqueous solution and your solute is not volatile, say it's a solid before you put it in there, okay? It's safe to say it's not volatile. So you can just heat it up or let it sit on the desk and you lose solvent over time. Then the solvent decreases in volume, but the solute doesn't. It becomes more concentrated. And we can see that from this slide because it's one of those solvents that is colored, solutes that is colored. This is probably copper sulfate. And as it becomes more concentrated, it becomes bluer. So sometimes there are indications as to the whether it's concentrated or not. We've been talking about, we sort of segued into aqueous solutions without telling you we were going there. But aqueous solutions are a major type of solution in chemistry and biology and medical professions. But there are non-aqueous solutions where the solvent, instead of water, you could substitute something else. And for organic chemists, that's a common practice. Because the solvent, if you're carrying on a reaction, the solvent may want to be part of the reaction. It may be preferred reactant. But the organic chemist doesn't want that, right? That messes up their product. So they generate solutions in a different solvent, a non-aqueous solvent, so that they don't have to deal with the water, which is really a reactive molecule in many cases. But the concepts are the same. You have the solvent major component, the solute or solutes minor components. That still holds, that terminology holds. Okay, we covered this one already. I'm not going to stop there. So we can theoretically, right, think of the dissolving of a solute in a solvent in three processes. Right? So let's say we have water is our solvent, and we're going to put a cube of sodium chloride. You ever look at sodium chloride with a magnifying glass? You know, accidentally, on purpose, spill some on the tabletop. Pull out your magnifying glass and look at it. They're all little bitty cubes. Right? So the arrangement of the sodium and chloride ions are such that they always give that cubic form. But if we're going to put that in water, what has to happen? We conceptualize it as a three-step process. Step number one, you got to break sodium and chloride bonds. In other words, you got to get the ions separate from one another. Now this works for sugar too. If you have sugar in there, they're going to be some intermolecular forces that hold the sugar molecules together. So you got to break the forces that are holding the solute together. Step one. Step two, you've got to break the water forces. The forces that are holding the water molecules together. You know that there are forces that do that. Otherwise, the water would just evaporate like that if there's nothing holding them together. Right? So you got to pull those water molecules apart, and sometimes we call that make a hole, or make holes. Lots of holes, spaces for these components to go into. So this is, we've defined endothermic and exothermic. Yeah. Endothermic is you put energy in. So this is an endothermic process. Breaking those bonds. This is an endothermic process. Right. Those two are endothermic processes. The third process is you create solvent solute bonds. In other words, you form bonds between the sodium and water molecules and the chloride and the water molecules, which is actually pretty easy to do because these are ions and the water molecule is polar. Right? It's slightly positive here, slightly positive there, and negative there. Okay? We talked about that, I'm sure. Polarity of molecules. So, this side of the molecule associates electrostatically with the chloride ion, and this side associates with the sodium ion. And when you form these bonds, this is an exothermic process. Right? When you form those bonds, the energy of that association lowers. So it has to give up energy. That's exothermic. But these two are endothermic. And when you put things in solution, sometimes you'll notice that they either get warm or they get cold. Right? Go to a hospital. I mean, hopefully you don't have to do it because you're sick. But if you do, if you've got a sprain and you want to put something warm on it, they'll pull out this bag, hot pack, and they'll break a capsule inside the bag and then mix it, and it'll get hot. Or if you've got a headache and you need a cold pack, they'll do the same thing with a different pack, and it'll get cold, and they'll put it on your head, and hopefully you'll feel better. But it's this process that determines whether it, on average, on the net value, is giving up energy, exothermic, or absorbing energy, endothermic. So if these two together are much larger together than this value, then the overall is endothermic and you have a cold pack.
Is that how those hot houses work?
Yes. Yes. I think that's ammonium acetate or sodium acetate, I think. You have a little clicker inside.
I don't know if it's a click or not. It's just like
Or you just shake it. Yeah. And you see the white precipitate form inside, right? It's clear first and then it gets white as the solute comes out of solution. And when it does that, it gets hot. And then to make it go back the other direction, you throw it in the boiling water and it goes back into solution, and then you pull it out and you can use it again. Yeah, but it's this three-step process, and the balance between the endothermic and the exothermic determines whether the overall process gets hot or gets cold. And that's what that whole slide's about. So what factors affect the rate of solution formation? Right? We've been talking about an equilibrium process up to this point. Doesn't matter how long it takes, just eventually, how much goes into solution. It might take 10 minutes or it might take 3 hours. Now we want to say, all right, how do we affect the speed? How fast something goes into solution. Particle size makes a difference. If the solute is very finely divided, when you try to put it in the solution, it'll happen quicker because there's more surface area for those bonds to form. We've got to break these bonds, we've got to break those, but these bonds form more quickly. because you have more surface area. Agitation will help. If you just throw your cube of salt in there and just let it sit, it'll eventually go into solution. But what's happening? Once the cube is in here, right, and it just sits there, you've got sodium and chloride ions accumulating around the surface, right? So they're obstructing the ability of water to get in there and remove them. Right? So it happens more slowly. It's by diffusion. The sodium ions and the chloride ions have to diffuse out to make room for the water to come in and take some more. But if you agitate it, now you've moved these out and you're bringing fresh water closer to the cube, and the solution happens faster. Temperature is another, right? That affects both the total amount that can go into solution and how fast it happens. And then there's one, the common ion effect. I'll write that over here. I mentioned earlier that the saturation point of the solute depends on what else is in there. So if you've already got something else in the solution, and particularly with ionic compounds, say if you have, you want to put sodium chloride in solution as a solid, you want to go into water, but the water happens to have sodium ions already from some other source. It doesn't have to be sodium chloride. It could be just sodium ions from, say, sodium acetate. If you've already got these in solution, then you're not going to be able to put as much of this in there. In other words, the sodium in here says, all right, I'm already occupying some of these, the holes that were created. There are only so much space for the rest of you. So it decreases the solubility and decreases the speed of solution for the new solute. Okay. Maybe that the statement says it better, but that's the way I look at it. And it's actually it's more pronounced for solutes that are only very slightly soluble. Good example is silver chloride. Silver chloride, based upon our solubility chart, remember that one with the gray, oh, I haven't shown you that yet, have I? That must be part of this discussion. It is, sorry. I'll show it to you in just a second. But we generally think of solubility as black and white. It's either soluble or it's not. And when in fact, there's a gray area between the two, where you can have maybe something that's only slightly soluble. And silver chloride is an example of that. But for these slightly soluble compounds, the common ion effect is more pronounced. So the solubility of silver chloride in this solution won't be affected because it's only sodium. But if there's a common ion in there, if we do have chloride ions in there, then they will compete and prevent more of this going into solution. It'll be less soluble, and it'll happen slower. Okay, solubility rules. First, we'll go with the general qualitative, and then we'll get more specific. The first one is called like dissolves like, and it depends on the polarity of the solvent and the solute. So when the molecules in a solvent are polar, that is, they have a slightly positive side and a slightly negative side to the molecule, we call that polar. The water is a perfect example. And the solute is also polar or ionic, then you're more likely to get a solution with those two. like dissolves like. They are alike, so they dissolve. But if they're nonpolar, for instance, gasoline or octane, which is the major component in gasoline, is nonpolar. If you want to put it in a solution of, if you want to add gasoline to diesel fuel, say, they're both nonpolar, so they mix together very well. But if you try to pour diesel fuel or gasoline on water, it'll just form a sheet. It won't go in a solution because polar solvents don't like nonpolar solutes. Okay, that's what we mean by like dissolves like. For other solubilities of ionic compounds in water, which is predominantly what we're interested in. In fact, let me check to be sure it's there. In your review document, you look on the last, there it is. The last page. There's your solubility chart. And it'll be in the next slide too, I hope. No, oh, we get the rules first. All right, if you are a chemistry major, you'd have to learn these rules. Right. Rule 1, 2, 3, 4, 5. What's soluble, what's not. Right? If it's any of the alkali metals, if they're the cations of the salt, then they're all soluble, always. If they're nitrates, NO3 minus, with any cation, they're always soluble. And then you have varying grades of solubility with exceptions to the rules. So you get these rules, and what I've done, and there they are. These are the solubility rules. If you ever have to use these rules, you won't have to use them in this class because you've got the solubility chart. But if you ever have to use these rules, they're set up so that if you have a conflict, right? If you say this rule applies to my solute and this rule also applies to my solute, the one above, the smaller number, right? If it's between 1 and 4, 1 wins. Okay? They're put in a hierarchy so that the first rules take precedence over anything below them and on down the list. Okay, here's your solubility chart. So how do you use it? Well, this is for ionic compounds only. So you're going to have a cation and an anion, a positive and a negative together in that compound. So when you try to put it in solution, or if the ions are in solution, say you've got a cation in this solution and an anion in this solution, when you put them together, what are they going to do? Are they going to stay in solution or are they going to drop out of solution? They're going to form a solid and precipitate, right? We did precipitates already when we were doing chemical, one of our labs. Well, you can tell in general. Now this chart assumes black and white, right? But we know that there are gradations in between. For now, this is all you need to know. Is it soluble or not soluble? Look at silver. Let me see. Let me use the cursor. Here we go. So it'll show up on the recording. If you use silver here, and you follow silver down until you reach chlorine or chloride, there it is. It's grayed out. That means it's not soluble. Okay. But if you go over here and say sodium, and you go down any one of these, they're all soluble. And that follows our first rule. All alkali metals, as the cations, with any anion, are soluble. But if you go over here, say lead 2+, you can go down to maybe iodide. Okay, not soluble. Or if you go ammonia, everything's soluble. So very often what we do is when we want to get chlorine in solution for an experiment, we put it in there as ammonium chloride. It'll go right into solution. And then silver, we may silver nitrate, right? Look at the nitrates. Right? There's silver over here at the top. Come on. There it is. Silver. And you follow it down to nitrate. There it is. It's soluble. So you can put silver nitrate in solution here. You can put chloride in solution. Actually, any form of chlorine you can put in solution, except for some compounds, but most. In fact, you can see, look at chlorine here. Go across silver, mercury, and lead. They're not soluble. So you won't want to use those compounds to put chlorine in solution, just sodium chloride or potassium chloride, whatever. Then when you mix those two solutions together, now you've got all those ions mixed together. What are they going to do? Well, the silver's going to find the chlorine eventually and drop out of solution. And what's left over? Well, if it's sodium chloride and silver nitrate, the sodium nitrate, look at that one, right over here. Sodium nitrate stays in solution. Right, so the only thing you get dropping out of solution is silver chloride. So that's how you use the chart. It's kind of like, well, they don't do it anymore, but used to be, you get these road maps that you could unfold. Don't know what I'm talking about, do you? Oh, you do? Okay, good. And then down in the corner, in the legend, they'll have distance chart. And it has all the major stopping points in that map. And down one side, there'll be a list, and down across the top or the bottom will be another list. And you just follow them up till they meet, and it gives you a value for the distance. That's kind of like that. In this case, you follow cations across the top, anions down the bottom, and where they meet, you see, is there a grayed out cell, or is it clear? And that tells you solubility. So, and that will be, the solubility chart will be on the exam, okay, along with the periodic table. Okay, greater difference in solvent polarity results in, oh, yeah, if there's the greater the difference in the solute and solvent polarity, the less soluble. Okay, so at first we said like dissolves like. We just said polar dissolves polar, nonpolar dissolves nonpolar, and they don't like each other. But in actuality, you see the relative polarity. If they're both strongly polar, then you get good solution. But if their polarity is further apart, say one's only slightly polar and the other one's very polar, then that solubility of the solute in the solvent would be less. And it has everything to do with that third process where you form the bonds between the solvent and the solute. See, how am I doing on time? 10:15. All right. I'm talking too long as usual. Let's see. And there's no buffer time, so I've got to finish it today. Which of the following ions are generally soluble in water, form compounds with lead 2+? And you just take that chart, right? Find lead 2+, go down, and you can see, check each one. Sulfur, chlorine, nitrate, sulfate. Sodium's a ringer. You don't form compounds with two cations. So the one in there that I know lead 2+ is soluble is nitrate. And the others, it's insoluble. And you can tell that from the chart. Okay, concentration. How do we express, remember that variable composition we know as concentration. How do we express the concentration of the solute in the solvent? Well, there are three primary ways. We're going to use the last one today, the molality. But before we get there, you can express concentration in terms of percent, which is grandfathered in. Percent, I've said this before, I think. Percent is difficult to deal with because there are no dimensions. It just means parts per 100 parts. Really doesn't say what the parts are. Only if you specify what the parts are. Is it parts of mass per 100 parts of mass? Or is it parts of mass per 100 milliliters of mass volume? Or is it volume? Right? So you need to specify percent unless the problem dictates that it has to be a certain percent composition, say mass or mass volume. Otherwise, it needs to say what it is. Molarity. Molarity actually is more useful. And I think there are subsequent slides on that. Molarity is moles per liter. Right, so moles of solute per liter of solution. Whereas molality is moles of solute per kilogram of solvent. Okay, and I'm going to explain the significance of those in just a second. All right, there's a slide on the difference, the problem with percent. Is it percent by mass, percent by volume, or a combination? Percent by mass, right? Mass of the solute per the mass of the solution. Right? It's not the mass of the solvent, it's the mass of the solution. So it combines both the mass of the solute and the mass of the solvent in the denominator. Okay, what's the percent by mass if you have 5.5 grams of glucose and 78.2 grams of water? Right, 5.5 grams of solute and how much solution? 78.2. Right, so you have to add them together to get the mass of the solution times 100. And that'll be your percent mass, 6.6%. Percent by volume, you need to know the volume. Well, in this case, you only need to know the volume of the solvent. So this is the one, actually, this is not used very much. But it's in here because we're talking about it. So what's the volume percent of methyl alcohol in enough water to give you 435 milliliters of solution? You know, that's not right. That should be volume of solution. That's an error. I'll have to fix that. Here it is. How do I know that? Because of the wording of the problem. The problem words it in terms of volume of solution. Okay. So I know that previous slide is an error. And that's how they calculate alcohol content by volume, ABV. Look on any bottle of wine or booze, and it'll be certain percent, like wines, they range, but let's say 15% ABV. That's alcohol by volume. I don't think they do wines in proof. I think they do hard liquor in proof. So well, we won't go into the history of proof, but if you see something that's 100 proof, what's its ABV? It's 50%. It's always half of the proof is the alcohol content. So 200 proof would be 100% ethanol, white lightning, whatever. I don't know, do they sell that in liquor stores anymore? Pure alcohol? Yeah. We used to use it in the lab, and it had to be pure. It couldn't be denatured for our research. And it always came with a tax tag strapped across the top of the bottle. Because even if you buy it for research, you got to pay that tax on alcohol. Mass volume percent. Okay, so here we have volume of solution and just the mass of the solvent. This one is more common. What mass of the solute and what's the volume of the solution after. This is very important, and this will segue into molarity, because when you add a solute to a solvent, say a solid to a liquid, the volume, or even a liquid to a liquid, the volume of the final solution is not additive. In other words, if you have 100 mils of solute and 1,000 mils of solvent, the final volume is probably not going to be 1,100 milliliters. It's going to be different, usually less, because those solute molecules are moving into the holes in between the solute, and that's volume. So it's probably going to be less. So that's why we specify volume of solution rather than some additive term. Okay, so this is just a comparison of doing the concentration of a given solution, the same solution in different terms. And when you have the concentration of a solution, it can serve as a conversion factor. Right? It's a quotient. Right? No. I get my math terms mixed up. Is it a quotient? Yeah, it's a quotient. Product is multiply. Quotient is divide. So it's a quotient. It has, say we have 6.6% ABV. Right? So we know that it's 6.6 milliliters of ethanol per 100 milliliters of solution. There, you've got a conversion factor. So if you're starting off with 500 milliliters of solution, over here as a multiplier, the solution cancels and leaves you with ethanol. And you can calculate how much ethanol is 500 milliliters, contained in 500 milliliters. So they're all conversion factors when you have concentrations. Okay, I'm going to skip that one. I'm running out of time. I'm going to have to skip that one too. We will, you'll get experience with this type of stuff working in the lab. Plus next week we have a review, and we'll take these problems in depth. Give you a chance to look at the review document and strain your brain a little bit. In fact, that's the best way to learn something is to stress your mind. If you have to struggle with a concept and eventually you get it, you'll never lose it.
So the week after next is the exam.
Yeah, week after next.
Do you have an extra copy of the lab from last week?
Yeah, it's right here. Yeah, it looks like there are 2 or 3 copies here. Yeah. Okay, molarity. We talked about those percent compositions. This one is much more useful, and especially in yeah, that's it. Especially in laboratory settings, and yeah, take one of each if you need it. That's how I worked each problem in the review document.
I have those.
Okay, good. You definitely want that handwritten one. Molarity. You're going to see this whether you're in the chemistry lab or any health professions or in the MLT program. You're going to get molarity, definitely. Molarity just means moles, and this is there it is. Molarity is number of moles, and that's my abbreviation for moles, per liter. And the volume has to be in liter when you do it this way. If you know the moles that are contained in this many liters of solution, and this is the solute, then you can calculate molarity. And the nice thing about it is, if you know the molarity, and you have, say, 1/10 of a liter of it, you can calculate exactly how many moles of solute you have in that 1/10 of a liter. By the way, how many milliliters would be 1/10 of a liter? There's 1,000 in a liter, right? So what's 1/10 of 1,000? 100, yeah. That's 100 milliliters in my example. All right. So if you have 1 mole of sugar and 125 milliliters of solution, then you would want, 1 mole per 125 milliliters is how many liters? Like that. And that will give you 8 molar solution. That's not unusual for sugar. You can put a lot of sugar in solution. For some compounds, that would be extremely high. And if you were calculating the molarity of, say, hydrochloric acid or sulfuric acid, that would be hazardous. So now if you have a 10 molar sugar solution, what volume of the solution do you need to have 2 moles of the sugar? So in this case, we take this expression, instead of writing liters in there, I'm just going to write volume, because we know it needs to be in liters. And the question is asking for what volume of solution. So we solve for volume. V comes over here, M goes over there. Right. Now we can substitute what we know. 10 molar, and you want to be sure you have 2 moles, right? So that's 1/5 or 0.2 liters. Oh, I animated this one. How about that? Okay. It's like any equation. You can solve for the unknown. Let's see. Now, for this one, say you have separate solutions of sodium hydroxide and potassium chloride. And they're made by dissolving 100 grams each of those solutes into and create 250 milliliters of solution each. What's the concentration of each solution? Is it going to be the same? I mean, you put the same mass in there, didn't you? But if we're calculating molarity, it's not the mass that matters, it's the number of moles. So sodium hydroxide and potassium chloride have different molar masses. So they're going to have different concentrations, even though we put the same mass in. And I hope I animated this one. Yeah. So the sodium hydroxide, notice we changed the mass here. We changed the mass to moles using that molar mass. And then we put that mass over the volume, which we have to convert it into liters. And that's what this does. So 250 milliliters is going to be divided into, this is in the denominator, but we're changing it to liters. That's what that does. I've done it all in one step. You can do it in separate steps. You calculate the number of moles of sodium hydroxide, then put it in your formula, and it'll give you the same thing. So that's a 10 molar solution for sodium hydroxide. Well, how about potassium chloride? There's the conversion factor. It's going to be a lower concentration for potassium chloride because potassium chloride has a higher molar mass. So it's 5.37, almost a half the concentration in molar terms. Okay, dilution. This may be as important as any other skill set you know. How do you prepare a known concentration of a solution once you already have the solute in solution, but it's at a more concentrated level? I used to work a lot in soil analysis. We would have various extractants made up so we could mix them with our soils and extract out elements and assess the amount. And you could, for us it was research, but for soil testing labs around the country, they tell farmers how much of each nutrient they have in their soil so they can supplement it if necessary. But we would have these, we'd have these working solutions that were a certain concentration of the solutes that we would use to extract the soils. But to make up a fresh batch like that every day would be tedious because it takes a while for some of them to go into solution, and it's just a mess. So what we did was we'd make up concentrated solutions and keep them in big jugs like this. And when we got ready to make our working solutions, we'd take a portion of that out and dilute it with more solvent. Well, how do you know you've got the right concentration when you do that? Okay, here's how. In that formula, let's go back to the formula. Right? And here's the concentrated solution, and you're going to put it into something of known volume, a volumetric flask, and it has a mark here. And that tells you that when your solution reaches that mark, you have exactly whatever. Let's just keep it simple, say 1 liter. You have exactly 1 liter in that container. All right? So you have a concentration over here of, well, let's do it this way. You have a molarity here for the concentrated solution. And you know your target is here, dilute. You know you want to go from this to that. Right? And you know that the volume of your dilute solution is this. Right? You want to know how much of this one do you put in there before you add the solvent, extra solvent. You want to know how much of the solute, what volume of solute. Actually, that's not right. Solution. Dilute, concentrated solution. How much of the concentrated solution you want to put in there before you dilute it. Now we know qualitatively that when we do that, the concentration of the solute is going to decrease. We're adding more solvent. But what's the one thing that's common to both of these? The number of moles. If you pull out a certain volume here, you've got so many moles from the concentrated solution. It's exactly the same number of moles going into the dilute solution, isn't it? Yeah, that's common. So if we set it up like that and we say, all right, let's solve for moles. Moles equals molarity times volume. Okay, so over here we have molarity of the concentrated one times the volume of the concentrated that you pull out is equal to the number of moles of the concentrated. And over here, you've got the molarity of the dilute times the volume of the dilute, and that's equal to the moles of the dilute going in. Well, they're equal. So this term is equal to that term. It's kind of like our gas laws, what we did before and after. So this one, concentrated is equal to this one, dilute. And it's like any equation. If you know 3 of those, you can solve for the 4th one. And the 4th one happens to be volume here. That's the unknown for this problem. We know that concentration, we know this concentration, we know that volume. We can solve for how much volume do you need to pull out of the concentrated and dilute. Okay? And sometimes it's written like M1V1 equals M2V2. So you can go backwards and forwards. I'm running short on time. Let me see how many more slides I got to cover. Quite a few. I don't want to rob you of this lab, but we do need to cover the material. Let's see how far we can get. I'm going to skip this one first. It's just working out the problem. And notice that the concentration, actually, this example was in molarity. But the calculation works for percent also. Depending on the concentration form you're using here, it might be different values here, but the equivalence is based upon how much of the solute is being brought over. Right? It's the same for both. So you can set up a formula here and a formula here, and they're both equal to the same moles. That's how it works. That's why they use C instead of M. Okay. I'm going to have to skip this one. Colloidal dispersions. All right. Remember I told you that solutions do not settle. Right? Suspensions settle. Solutions do not settle. Well, there's another class that doesn't settle either. They're called colloids. They're based upon particle size. If you eat Jell-O, you like Jell-O, you're eating a colloid. The size of the molecule is small enough so that the kinetic energy of the solvent is sufficient to keep it suspended. But we can tell the difference between a colloid and a solution with the Tyndall effect. You just shine a light through it. Shine a light through Jell-O and you see the beam, right? Okay. But we can't call them solvent and solute because it's not a solution. So instead, the dispersed phase is the solute equivalent. And the dispersing medium is the solvent equivalent. Okay. It's really just a matter of terminology. Well, it's not just terminology, but we have to use terminology because it's not a solution. And you can have lots of different types of colloids too. Smog is a colloid. It's suspended particles that don't settle out, but it's bad. And here's the description of the Tyndall effect. We won't have to spend time here, except long enough for it to be recorded. And there you see the solution is on the left, the yellow one, and the colloid or the suspension, whichever the case may be, is on the right because you can see the light beam traveling through it. That's because those particles are not in the solution. They're not in those holes that we created. They're just suspended. Suspension, right? I mentioned that before. That's a heterogeneous mixture that contains those dispersed particles, and most of the time they're heavy enough to settle out over time. And if they don't settle fast enough, how do we make them settle faster? Stick them in a centrifuge. Right? You can simulate gravity of more force in a centrifuge that you don't get by just sitting on the table. Right? So centrifuges hook up. I mean, these little centrifuges over here against the wall, medical centrifuges, they might produce 10, 20, maybe 30 Gs, 30 times the force of gravity. But we had a couple of centrifuges in the lab I worked in One, they were both refrigerated because this generates a lot of heat too when it spins. But they would go 5, 6, 7,000 RPM, produce 100, 200, 300 G's force. Then we had an ultra centrifuge that would go 10,000, 15,000 RPM, and it would produce a lot more. But it was evacuated. I seal the lid and start the pump, and it'd pull all the air out so that it wouldn't be as much air friction resistance. It was pretty sensitive. We had to have regular contract maintenance on it. But it would settle things out. I mean, if they were very stubborn, you could put them in that centrifuge and it would drive them to the bottom of the tube. You had to choose your tubes wisely too. Because they're under a lot of force as well. You don't want to put a tube in there that can't stand it. So very often our tubes would be made out of pure silica, which is quartz. Okay, property comparisons of solutions, dispersions, and suspensions. I'm going to let you look at that that came out of your textbook. In fact, all these tables did, except for that one. The one for the solubility chart, I imported that from some other source. You may not find that in your textbook. You may, but I haven't looked at your textbook in a while, so I don't know. Okay, let's skip that. Colligative properties. A colligative property is physical. It doesn't reference any known chemical changes. And it's of solutions, and it basically depends, the colligative property, the variability of that property, depends only on the concentration of the solute particles in the solution. Okay, so that's nice. That's really good, because if you don't know what the compound is that you're putting in solution as the solute, then you may be able to use a colligative property to find out how many moles there are. Right? And if you get the mass before you put it in, and you can determine from the colligative property how many moles you just put in, mass and moles, you can do the molar mass of that compound without even knowing what it is. So we did empirical formula and molecular formula before, calculations, didn't we? Did we do those earlier in the semester? Those molar masses of the compound were determined using colligative properties. We're going to use one of them today. It's called freezing point depression. And we're going to know what the compound is, but we're going to use the colligative property to determine its molar mass, and then compare it to the accepted value, of course. Okay, these four are the most common. I mentioned freezing point depression here, the third one. You can also elevate the boiling point by adding a solute. Freezing point depression, everybody's got one of those in their radiator in the car. You add antifreeze, that lowers the freezing point. So when the weather gets really cold outside, the water in your radiator doesn't freeze and rupture your, hopefully just your radiator, but if it freezes in the engine, it could crack your block too. So we use that colligative property for our automobile engines and their coolant. Elevation of boiling point. You can increase the boiling point. Say you live in Denver, Colorado. You're a mile high, and the boiling point of your water now is not 100 degrees. It may be 85 degrees. Well, your eggs are going to cook slower because the water's not as hot. You can't get it hotter because of the elevation. So you throw some salt in there, you increase the boiling point of your water, now you can cook a 3-minute egg in 3 minutes. I don't think I'd like a 3-minute egg. I like mine about 5 to 7 minutes. 3 minutes too runny. That's another colligative property, boiling point elevation. Vapor pressure lowering. If I measure the vapor pressure of pure water at room temperature, it'll give me so many millimeters of mercury, like 22, I think, millimeters of mercury. But if I put salt in there, the vapor pressure will decrease. And that'll keep my water from evaporating as fast, if that's my objective. I won't go into why, but it will happen. You can lower the vapor pressure by putting a solute in there. And that's in the case where the solute is not volatile. Right? There's a complication if your solute is also volatile, like booze. When you throw ethanol in water, both of them are volatile. So now you've got a combination effect that you have to take general chemistry to deal with. Fortunately, I don't think you guys will have to do that. And then osmotic pressure. So what's osmotic pressure? Anybody have biology? They always talk about osmosis in biology class. Or anatomy and physiology. They'll talk about it there too. And the example there is given in terms of the cell. What does every cell have in common with every other cell? It has a membrane. Something that tells you that this is the cell and this is the environment. It separates it. Well, that cell is not impervious. I mean, it's porous. And it's porous to very small molecules and usually to water molecules too. So if you put your cell, which is at a certain molar concentration inside the cell, and then you have something out here that's at a different concentration, the molarity of the solution, then you can tell, based upon the comparison of these concentrations, which way the water is going to move. Now, if the cell is isotonic to this, or if this is isotonic to the cell, then no water is going to move. That's the ideal. And that's you want isotonic solutions if you're going to inject them in your patient. Right? Because if you inject the wrong concentration in your patient, you could kill them. So an isotonic solution says there's no movement. A hypertonic solution is one in which this one, the solution concentration is greater than the cell concentration. I better write this. Okay, what does that mean? Well, the solute can't move across the membrane, but water can. So which way is water going to move? It's going to move from the higher concentrated region of solvent to the lower concentrated. So if this is hypertonic, that means it's higher concentration of the solute, lower concentration of the water. So the water is going to move this way.
What we've been doing in college.
Yeah.
The last semester had some.
So did you look at the cells under a microscope?
Yeah, we do that, but not this particular. We're just
Oh.
talking about hypertonic and hypo.
Right. So hypotonic,
Goes into the cell, right?
right, means that the molarity of the solution is less than the molarity of the cell. So what that means is the concentration of water out here is higher than in the cell, and the water goes this way. Okay, what effect does that have on the cell? It would burst, right, if it goes this way. And this way, it's what we call, yeah, there's a term for it, crenulate. It's kind of like crumples. It's called crenation. Yeah.
What's it called whenever the cell is like kills itself, basically? Is it apoptosis?
Oh, if it's a programmed death, yeah, apoptosis. You see that, I guess in mammalian or animal systems, but I think of it in terms of leaves dropping in in the winter, in the fall. Right? There's a layer of cells holding the peduncle of the leaf to the branch, and when it's time to die or to shed the leaves, those cells have programmed death. They die, breaks the contact, and the leaves fall. Yep. Okay, so osmotic pressure is the difference between this solution and the cell. If it's a higher osmotic pressure than in the cell, then that means hypertonic. So actually it's relative to, this is a bad example. Let me see if I've got a better example, a chemical example. No, it doesn't have it. See, wrong course. The way it's measured, one way it's measured is with a U-tube. And you have a membrane here. And this one is, say, the concentrated solution, and this is the dilute solution. Or it could be distilled water. And if this is the concentrated solution, same volume to begin with, then this is concentrated. Water's going to move that way, right? Into the concentrated solution. And this is going to rise, and this is going to drop. The difference in pressure from here to here is the osmotic pressure. Because it goes up here and stops. Because it reaches a certain point, and they don't have to be the same concentration when it stops. There's enough pressure here forcing water back that way. Now the processes one way are at the same rate as the other way. That's osmotic pressure. So that's why we say the hypertonic solution has a certain osmotic pressure. And it's usually based against pure water. Okay, now let's see how we're going to use them. Well, this one refers to the, let's see, did I talk about vapor pressure? Yeah, vapor pressure. This one is Rayleigh law, which is for vapor pressure. Okay, Rayleigh's law. This is the vapor pressure of the solution. In other words, you seal the vessel with a solution in it, and you measure the pressure at equilibrium in the headspace. And you can calculate that if you know the mole fraction of the solvent. That's what that big X means. So what's mole fraction? Did we talk about that? We didn't talk about that, did we? Mole fraction. It's the number of moles of, in this case, the number of moles of solvent in the total moles. Of solution. That's it. It's just a fraction. So it's always going to be less than 1. Unless it's a pure solvent, and then it'd be 1. But that would kind of defeat the purpose. The mole fraction of the solvent, and this is the vapor pressure of the solvent under standard conditions, or under the same conditions, both sides. So if this tells you what fraction of the solution is the solvent, and this is the pure solvent pressure, that will tell you the final vapor pressure of the solvent. This is just a pictorial representation. This is the pure solvent, and this is the one with solute in it. There are a couple of factors that are decreasing the vapor pressure. That is, fewer molecules from the solvent are entering the vapor phase. And 2 reasons. One reason is there are solute molecules at the surface where you get the evaporation taking place. They're just hogging space. So there are not as many solvent molecules there at the surface to evaporate. Right? So it's a competition. The other factor that can come into play is any interactions between the solvent and the solute molecules. If the solute and the solvent interact strongly, then they're going to depress the ability of the solvent to evaporate. You're going to hold it back. So you get those two factors working. Boiling point elevation. Right. This is the formula for boiling point elevation. You know, we didn't talk about M. Okay, I'm going to talk about it now. The little m, not the big M. Molarity. Little m is molality. So you can tell change in the boiling point temperature, right? That is final temperature minus initial temperature. Will be, let's see, final temperature should be higher. Yeah, minus initial will give you a positive value. That's okay. That difference, that's important. It's not the absolute temperature, it's the difference in temperature, is equal to this factor, this K value. And this is peculiar for the solvent. It's different for every solvent. Right, so water will have one. In our case, lauric acid will have a K value, and that's given in your method. And then this is the molality of the solute. Okay? So what's molality? Molality, little m, is like molarity, only it's moles of solute per kilogram of solvent. Okay? Instead of a liter of water, we would put a kilogram of water. If we were dissolving so many moles and putting it in, the difference is twofold. It's both mass instead of volume, and this is only the mass of the solvent, right? Not the total volume of the solution. Okay, those are the two differences. Why do we use mass here? The colligative property is a change in temperature. If we used volume and we change the temperature, the volume is going to change. So the volume is a moving target. Okay? We need something that's stable at temperature change, and that's mass. That's why molality works here, and molarity would not work, because molarity is in terms of volume. Okay. So that's how we do, the KB for water is 0.51 degrees C per molal. So you find the molality. Actually, we're going to do it backwards. We're going to determine the temperature change between pure solvent and solution. That's what this means. The difference in temperature for the boiling point of the pure solvent versus the solution. And then we know this value, and we can solve for that value. What is the molality of the solute? But we're not going to use boiling point for ours. We're going to use freezing point. But they're very similar. Freezing point depression. I need a new marker. Let's see if one of these will suffice. Freezing point depression is similar with a different constant, but we're still using the molality of the solute. Okay? So we need to determine how many degrees is the freezing point depressed. In this case, if you subtract the initial from the final, right, right? Because the final is less than the initial, you're going to get a negative number. So in reality, we only use the absolute value, right? It has to be a positive value. So whatever the temperature is depressed for the freezing point of your solvent by adding the solute to it, that's the difference that you're looking for here. So that's why we have to run our experiment twice. We have to determine the freezing point of the solvent, which is lauric acid. Then we put a certain mass of the benzoic acid in it, mix it up, and determine its freezing point again. And its freezing point should be less, and the difference goes in here. And then we have a value here for the lauric acid. Water is 1.86 according to this slide, but we have a different value. I think it's 4 point something in your method for lauric acid. And then we can solve for the molality. So that gives us the molality of the, and remember, molality is moles of solute per kilogram of solvent. So we have to weigh the lauric acid too. We have to know what its mass is, right? So we can go in here. And then we calculated molality from this equation. Now we can solve for the number of moles of solute. And since we weighed the benzoic acid before we put it in, and now we know the number of moles, we can calculate its molar mass, right? I'm sort of doing a lab prep at the same time here. Those are colligative properties: boiling point elevation, freezing point depression. Osmosis. We're going to do a lab where we use osmosis. Which one is it? It's the next one. I need to hand that out, though. I probably ought to do it since we might. Osmosis. The cell membrane, we often treat the cell membrane as a semi-permeable membrane. Semi-permeable is a term that refers to the passage of small molecules, particularly water, and most of the gases will flow through a semi-permeable membrane. And then there's also the selectively permeable membrane. By comparison, the selectively permeable membrane can be almost anything. They can devise these polymers that are treated a certain way to let some molecules go through and others not. And the one we're going to use next week is selectively permeable for size of molecules. So the really big ones won't go through, but the small ones will go through. And that'll make more sense once you study the method. But for practical purposes, the semi-permeable membrane we treat as if nothing goes through but small gas molecules and water. And we just stop it there. That's a lesson in terminology only. Oh, here we go. Process of osmosis, where we determine the osmotic pressure of a liquid. It shows that this is the pure solvent, and this is the solution under investigation, and we've got a membrane right down here at the bottom. Okay, so what's going to happen is the solvent is going to move from this pure solvent and go into that, and it's going to go and create pressure, back pressure. As it gets higher and higher and higher, there's going to be more and more pressure against that membrane from the solution. And at some point, there's enough pressure that drives the water molecules back through the membrane at the same rate as they're coming in. So at that point, it stops. And the difference between the height of the solution and the height inside the tube, that's a measure of the osmotic pressure. Now, if you say hook the top of that tube up with a gas line or an air compressed air line and start applying pressure on the surface of that liquid, you can drive the solvent molecules back the other direction through the membrane. So we add pressure to it. We exceed the osmotic pressure of the concentrated solution, and we drive the solvent molecules back through the membrane. That's the whole concept behind reverse osmosis and purification of water from saltwater sources. Reverse osmosis works. We used to use it in the lab I worked for, in the USDA. We had a reverse osmosis thing for the whole building, and it would take city water and pre-treat it by running it backwards through the membranes under pressure, and give us purified water up to a certain level. And then each lab had its own separate polishing unit that would finish it off and give us ultra pure water. But you can use it on a grand scale, and as long as you've got enough energy, cheap energy, like some of the Arab countries do that don't have a lot of fresh water, they can take seawater and burn their oil and make energy and drive the reverse osmosis will give them their purified water. But the key is cheap energy, right? That's people that rely on this method right now in this country are in deep trouble because the energy costs so much. Okay, this is just an illustration of what happens in a semi-permeable membrane. Let's see, which one is which?
So are we doing the molar mass last day?
I hope so. Let's see, we've got till what, 1 o'clock?
Yeah.
Okay, we might be able to make it. Yeah. It doesn't take a long time. It just, if you're new to it, it might extend the time required.
I just didn't know, because you said you might cancel stuff.
You what?
You said earlier that you might cancel.
Might, yeah. I don't want to, but I might have to. It depends on whether I talk faster. Okay, this is an illustration of reverse osmosis. If you put pressure on that liquid, it'll drive the solvent back through the membrane. And for reverse osmosis in drinking water, of course, that solvent is water, and you want to leave primarily sodium chloride behind. It creates a brine. And there are various methods that have been devised, engineered to be sort of a continuous flow. So you have a countercurrent flow through these membrane tubes, and you drive the brine through the inside of the tube, and the outside of the tube has pure water surrounding it. That way you can continuously go through and they have stacks and stacks and stacks of these things. If you ever see pictures, you can probably Google it and see a facility. And really, besides the cheap energy required, the real problem is the longevity of your membranes, because they have a limited life, and you have to keep cycling them in and out. This is a neat problem. I'll just give you the shortened version. I often wondered, even as a kid, I wondered, how does water get from the bottom of that big tree to the top? Because it does. There are leaves up there, and they got to have water. And it doesn't come from the air. It has to come through the roots and up through the xylem of the tree. And if the tree is like 100, no, some of them are 200, 300 feet, right? Some of the sequoias are 300 feet tall, right? That's too high for water to rise under 1 atmosphere pressure. Right? If you make a barometer with water instead of mercury, like Torricelli's barometer, make it with water. You can't get it any higher than 33 feet with 1 atmosphere pressure. right? So that's the limit. And then for a while I thought maybe there's suction, right? The leaves are evaporating water, maybe it's causing a suction to pull it up. That didn't work either. They've done experiments to disprove that one. So the other thing is, right, is there enough pressure at the bottom to drive the water to the top, right? And what would be that pressure? We just talked about it, osmotic pressure. If the sap inside the tree is concentrated with very low water content, and the water outside the tree, while not pure, it's less concentrated, then it's going to move into the roots, right, under osmotic pressure. And is that enough pressure to drive the water to the top of the tree? Well, it's been measured. The osmotic pressure in roots has been measured at 20 atmospheres. That's pretty high. Is that enough to drive water to the top? And that's what these calculations do. Right? I just find out how many millimeters tall is the tree. That's what that calculation is. And I say, okay, under 20 atmospheres, how high would water rise? Well, you need to know how much is an atmosphere in millimeters of mercury, and then millimeters of mercury to millimeters of water. Right? So that tells you how high 20 atmospheres will drive water to the top. It's 10 to the 5th millimeter column of water, and the tree is only 10 to the 4th, well, just under 10 to the 5th millimeters high. So actually, the water will go 600 feet. And it only has to go 300. So osmotic pressure is the reason water will go to the top of the tree. Okay, here's another term, osmolarity. One osmole is related to molarity, but it's dependent on what is the what actually goes into solution, right? And this is how I illustrate it. If you've got sodium chloride here, you think it's in solution. What actually happens is it breaks apart. Now, the osmotic pressure is dependent on this side, not this side. Right? This is like 1 mole. But here we have 2 moles of particles that are determining the osmotic pressure. So we need a correction factor. So if we know the molarity of this one, or they use molality. No, molarity. If they know the molarity of this one, then this factor over here, I equals 2. The osmolarity is actually equal to 2 times the molarity. Because this is the molarity of the whole structure, the whole compound. This is actually the molarity of the individual particles in solution. Right, that's the shortest version I can make. So the osmolarity of 3 molar sodium chloride would be what? 6. 2 times 3. Okay, we talked about this already. Hypotonic solution. The solution outside the cell is lower in concentration of solute than inside the cell. Hypotonic. That means that the concentration of solvent is higher. So the solvent's going to move into the cell. Yep, into the cell. Hyper is the other way around. You don't have enough solvent outside the cell, so it sucks solvent out of the cell. And it what? Yes, they crenate. They crinkle. All right. Isotonic is the ideal. And that's the one you want for your patient before you put an IV in. If you put a hypotonic or a hypertonic solution within limits, it could kill them. Now, sometimes they do it on purpose, but that's a medical treatment, and it depends on their condition. Oh, I got pictures. So the one on the left is hypotonic. It's going to explode, maybe. And the one on the right is hypertonic. You'll also see these terms, D5W. You ever seen that? All EMTs know what D5W means. And they have it in their vehicles, right? If they want to start an IV, if the patient is losing fluids and they can't stop it, like they're bleeding internally, and they want to replace enough fluid so that the heart will keep working, then they'll connect D5W until they can get them to the hospital. D5W is dextrose 5% by weight. That's what D5W means. Now, they have to be careful, right? So if you're a severe diabetic, you need one of those bracelets. Because if they see one of those diabetic bracelets, they're not going to hook you up to dextrose. They could put you in a coma before they get to the hospital. So they have to substitute a different solution. And that is isotonic to the cells. D5W is isotonic. Oops. Watch my step here. And 0.9% sodium chloride is isotonic. So that would be 1.8% particles, because you have to multiply it by 2. Now, this wouldn't be ideal for your patient, but on a short-term basis it might be okay, because it's going to flood their system with sodium. It's not as bad as chlorine, because your body doesn't tolerate chlorine as much as it does sodium. So you don't want to do that for a long period of time. And that's why solutions that they give you in the hospital, if you're going to be on them for a few days, have other things in them, like lactated ringers, they call it. Has a mixture of different things in there that are more compatible chemically and physiologically than either one of these. Those are kind of emergency solutions. But they are isotonic. Let's see. All right. This gives you an NIH report here on the dangers of 0.9% sodium chloride. And it talks about what's normal for the body, what's physiological sodium content and chloride content. And it says you're way off, especially on the chloride, if you want to take a peek. Okay. Osmolarity, just say, all right, when it goes into solution, how many particles does it make per mole? Sodium chloride makes, for every 1 mole of sodium chloride, you make 2 moles of particles. So your factor is 2. If you had calcium chloride, it'd be calcium CaCl2. So your correction factor would be 3. 1 calcium and 2 chlorides. Oh, we might be done. I'm not too far behind. I'm going to skip these concept questions because we're going to talk about this stuff next week when we do a review. You're welcome to look at them if you want to. Right, there's the animation on the solution to question 1. There you go. I'm going to leave it on there long enough to get a good recording in case you want to look at it later. It's assuming my recording's working now. It's not zoomed. Did you hear from anybody else? Okay. They're probably wondering what happened.
No problem.
Unless they check their email, and then they know. But it's been my experience that most students don't check their email but maybe once a week. Okay, there's the end of our slideshow.